Imagine a car that can drive from Paris to Berlin on a single charge, without a battery the size of a shipping container. For decades, we've been stuck in a trade-off between weight and distance. Every modern EV relies on a delicate balance of chemistry and physics, but we've hit a ceiling. Traditional lithium-ion cells are reaching their theoretical limits, leaving engineers searching for a way to pack more energy into the same footprint. But in February 2026, Ganfeng Lithium announced a breakthrough that changes the math entirely: a 650 watt-hour per kilogram semi-solid-state battery. This isn't just a small step, it's a massive leap in energy density. To understand why this is so difficult, we have to look at the anode, the part of the battery that stores lithium when the car is charged. In standard batteries, we use graphite, which is reliable but bulky. If you want more energy, you'd think you could just use pure lithium metal. It's the ultimate anode material, but it has a fatal flaw. It expands and contracts violently during every charge cycle. This expansion is like trying to inflate a balloon inside a steel box. Eventually, the pressure becomes too much, the materials crack, and the battery fails. This is the strain problem that has haunted engineers for years. Ganfeng's solution is a masterpiece of mechanical engineering. They've developed what they call a zero-strain lithium alloy anode. Instead of pure lithium, they've created a specialized metallic matrix. By alloying lithium with specific elements, they've created a structure that can hold vast amounts of energy while barely moving. It's the difference between a sponge that swells and a rigid frame that stays put. This mechanical stability is the key to reaching 650 watt-hours per kilogram. It allows for a much thinner, lighter anode that doesn't need heavy reinforcement to stay together.
But the anode is only half the story. To make this work, Ganfeng had to move away from the liquid electrolytes used in your phone or current EV. Those liquids are the reason batteries can catch fire if they're damaged. In their new 650 watt-hour per kilogram cell, they use a semi-solid structure. Think of it like a hybrid between a liquid and a solid, a dense gel-like matrix that provides the best of both worlds. This semi-solid layer acts as a physical barrier, preventing the dangerous dendrites from growing and short-circuiting the cell. It's a mechanical shield built directly into the chemistry.
The result of all this engineering? A battery that can store nearly 3 times the energy of the cells in a standard Tesla Model 3. This changes everything about how we design vehicles. We're no longer talking about 400 or 500 kilometers of range. We're looking at a 1,000-kilometer reality in a standard-sized car footprint. That's the distance from New York to Charlotte and back on one charge. But how does the zero-strain anode actually work at the molecular level to prevent that expansion? To understand that, we need to dive into the physical mechanics of the alloy itself. In a typical lithium metal battery, the anode is like a parking lot that grows a new floor every time a car arrives. This constant physical growth creates massive internal stress. Ganfeng's zero-strain alloy works differently. Imagine a parking lot where the cars slide into pre-existing rigid slots that never change size. The cars are there, the energy is stored, but the building doesn't move. By limiting the expansion to just 3 to 5%, engineers have solved the primary cause of battery degradation. This isn't just about range, it's about a battery that can last for decades. The secret lies in the host material. Ganfeng uses a proprietary blend of metals that form a rigid, conductive framework. This framework acts as a cage for the lithium atoms. When the battery charges, the lithium ions don't just pile up on the surface. They migrate into these specific sites within the alloy lattice, filling the gaps without pushing the atoms apart. This is a feat of precision manufacturing. The alloy must be uniform across the entire surface of the anode, down to the nanometer scale, to ensure the stress is distributed perfectly. Traditional anodes crack because the expansion is uneven. Some areas grow faster than others, creating hot spots of mechanical tension that eventually snap the material. Ganfeng's alloy eliminates these hot spots. Because the expansion is limited to 3 to 5%, the internal pressure remains constant. It's like a bridge designed to handle a massive load without bending an inch. This mechanical quietness also makes the battery much safer. Without cracks, there's no place for the electrolyte to react unexpectedly with the lithium, preventing the runaway heat that leads to fires. But how do you get the lithium ions into that alloy quickly? That's where the semi-solid electrolyte comes back into play. It acts as a high-speed highway for ions. In a pure solid-state battery, the interface between the solid electrolyte and the solid anode is like 2 bricks pressed together. It's hard for ions to cross the gap. By making the electrolyte semi-solid, Ganfeng has created a wet contact point. It flows into every microscopic nook and cranny of the alloy anode, ensuring a perfect connection. This perfect contact is what allows the battery to charge so fast. Even with its massive 650 watt-hour per kilogram density, the ions can move in and out of the anode with almost zero resistance. It's a hardware solution to a chemical problem. By controlling the physical movement of the atoms, Ganfeng has unlocked a level of performance that was previously thought impossible. Now, let's look at what happens when you take this technology out of the lab and put it into a real-world vehicle. The implications for the future of transport are staggering. The transition from liquid to semi-solid is more than just a chemistry change. It's a complete redesign of the battery's internal hardware. We're moving from a bag of liquid to a solid-state sandwich. In a standard cell, you need heavy plastic separators and steel casings to keep the liquid contained and the electrodes apart. With a semi-solid, the electrolyte itself provides structural support. This allows engineers to remove dead weight, the parts of the battery that don't actually store energy. That's how you jump from 250 to 650 watt-hours per kilogram. For a vehicle like a standard SUV, this means you can either double the range or halve the weight of the battery pack. A lighter car handles better, stops faster, and wears out its tires more slowly. But the real magic happens when you keep the battery size the same. A 1,000-kilometer range eliminates range anxiety forever. You could drive for a week on a single charge without ever thinking about a plug. This isn't just a luxury feature. It makes EVs viable for long-haul trucking, emergency vehicles, and regions with sparse charging infrastructure. It's the final piece of the puzzle. Manufacturing these cells is the next big challenge. Ganfeng is using a high-precision stacking process rather than the traditional winding method used for liquid cells. Winding a battery like a jelly roll creates stress at the corners. Stacking them like a deck of cards ensures that the zero-strain anode stays perfectly flat and functional. This stacking method also allows for better cooling. Heat can be drawn away from the flat surfaces much more efficiently, allowing the battery to maintain peak performance even under heavy loads. As we look toward the end of the decade, the 650 watt per kilogram mark will likely become the new gold standard. But Ganfeng is already looking at how to scale this to millions of vehicles. The engineering we've explored today, the zero-strain alloy, the semi-solid matrix, and the stacked hardware, is the foundation for a new era of energy storage. It's a reminder that the biggest revolutions often happen at the smallest scales. By solving the mechanical stress of a single atom, we've unlocked the ability to move the entire world. Next time you see an electric car silently glide past, remember the incredible mechanical dance happening inside its floorboards. The struggle against strain has finally been won. We are moving into a world where range is no longer a limit, but a choice, and it's all thanks to the clever engineering of the zero-strain anode. The 650 watt-hours per kilogram battery isn't just a lab experiment anymore. It's the hardware that will power our future. And now you know exactly how it works.